So today we're going to talk about scalings and making a model non-dimensional. So the model we have started last time was about the fall of an object, right? So we just release a rock, let's say, into a well. And basically we know from calculus, we're told that, and actually from Galileo Galilei, like what, 500 years ago. So he did experiments and he noticed that, the objects always, have the same acceleration, right? No matter what their weight is. So, and the acceleration is constant. And then if we, use Newton's calculus, we end up, with this kind of law of the fall, or if you want, basic thing is that, oh, we have, the acceleration in time is constant and is minus g 9.8 meters per second. Fine. Okay, so that's one model. Okay, but then we know from Newton as well that if we have two objects of different masses and idealized as mass points, anyhow, the force in between them is directly proportional with the product of their masses, which is up here on top, right? And the gravitational constant, and then the distance inverse proportional to the distance squared. So long story being short, making it short, the model in this, for this rock falling into a well, if we are to listen to Newton, would be this wonderful equation here that we wrote last time. So it would be the acceleration d2h and dt2 equals gm, so a constant, right, on top, over the radius of the Earth plus h, the distance above the Earth that the rock has, right? So it would be the overall the right, the distance from the rock to the center of the Earth. So we have two models here, right? So we have one, right, with that looks more complicated if you want, and one very simple that we know from calculus, right, and physics from Galileo. And the question is, what's going on here? Which one is correct? If they're both correct, this means that they don't really, they fit only certain scales, whenever we're far in the space, probably we would take this model here, whereas locally on the Earth, we would take this one. So the purpose is to understand how this is obtained one into another and what's going on here, okay? So this thing involves basically considering the model with scale. So here, what we did last time, we rewrote the model, we kind of massage it, as they call it, and we ended up with, where is it? With this system from last time. And then I rewrote it here. And then I was saying that we introduce a characteristic time and the characteristic distance, which we don't know what they are a priori. That's what I don't want to do, okay? I want to kind of deduce them with you, okay? And then basically what we do, we change the variables in the system. So from t and h, we go to a t bar and an h bar. So I repeat, TC and HC are characteristic scales and they will be decided later. They're constants, okay? And then when we do this change of variable, we did yada, 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 right? We again massage the system, and I think that's the last page. Yeah, we ended up here, okay? So what I will do, I will take this model on the next page. So there's the object of interest. The question now is, what should be TC and what should be HC, so that when scaling this model, we end up with something that is realistic, okay? So that's the purpose of this exercise now. So that's what I'm gonna do, okay? So I'm gonna write it on the next page. I have here everything prepared nicely. So let's start, okay? So this is in the continuation from the notes from last time. So here is again the model. Okay, there's that factor in front, 1 over. So as I said, it's a bit, the original model was a bit massaged, as it's called, in order to bring it to, so this is a bar there, right? A form that we can start working on. Okay. Okay, so let's call this one. Okay, maybe I'll do it nicer. 1. All right, so now we have choices for, so we need to choose TC and HC so that we end up, if you want, with a realistic model. Okay, so basically realistic, they're all realistic in a way, it's just they're different for different scales, right? You know, so okay, I'm gonna rewrite this word because I don't like it. Okay. So this is meaning that is appropriate for the context. Okay, the context described. Okay, whatever, blah, blah, blah. Okay, good. So 1, okay, we start, you know, looking for choices. 1. Okay, so we observe, for instance, that, so I'll start with an observation that R over V naught, right? This would be what? The time. This would be the time that, you know, if velocity, you know, if we would just go towards the center of the Earth, or, you know, the time to go over the distance R with constant velocity V naught, right? Time of covering the distance R with constant velocity or constant speed. Everything is in speed because it's one dimensional, anyhow. V naught. Okay, so it's like an average time, if you want, if the velocity wouldn't change. All right, so maybe I'll choose this one to be, so I'm gonna choose, okay, so I'm gonna choose, I'm gonna try, right? So it's like a try. Okay, TC equals R over V naught. Okay, so that would be the characteristic time that I'm choosing. And then now for a characteristic scale, now this one will always be a kind of easy to, well, it's kind of natural to choose it to be R, right? Especially that it shows here in this, you know, so H bar has no dimensions and HC over R, right? This is length over length, you know, so I might just make it 1, you know, so to make it 1, you know, I should choose HC to be R, right? Or if you want, you know, the characteristic length, you know, it's in tone with the characteristic time that we choose, right? Which the characteristic time is, you know, the time would take to, you know, go over distance R with constant velocity V naught. All right. So now this being said, what I'm going to do, I'm going to go back into 1, and wherever I see TC and HC, I'm going to put these numbers or these symbols. Okay. So substitute into 1. Now I believe that you can do this substitution. So blah, blah, blah. Okay. And we end up with, actually, this should be a bar here. So, you know, something, I will drop the bars in the writing everywhere. So drop the bar notation into 1, okay? But it's just I'm dropping the bar notation, not that I'm dropping the meaning of H bar. Okay, so I repeat, I'm dropping the bar notation because then I'll just bar everything all the time. But the meaning of H would be that one of H bar, and the meaning of T will be the meaning of T bar, right? So it's an adimensional length and an adimensional time if you want, okay? So dropping the bar notation and doing this substitution of these guys there, we end up with DH2, DT2 equals minus RG naught. No, there is no naught. RG, right? G is the acceleration, over V naught squared, 1 plus H squared with H in 0 and DH dt in 0 equals, so I repeat, all I'm doing, I'm substituting TC and HC with what they are there, right? So when I'm doing the job, blah, blah, oh, it's going to end up to be 1. Okay. Now that's an interesting model. Okay, you don't have to do anything. I'll just flip the page and write it again so we can look at it, okay, and discuss it for a second. So I'll just rewrite it because I need to see it. Squared. Okay. Okay. So now I'm commenting on this model, right? So it could be like this. So this R and G, so remember, R is the radius of Earth, right? Idealize the perfect sphere, right? G is the gravitational acceleration. My point is that these things are known, right? V naught, right, is the initial velocity, right? So they're all known. So being known, I can actually compare them to see what is this this ratio here that shows up here. So I have 3 possibilities, right? So if this ratio, right, is much less than 1, so i.e. Rg is much less than, right, V naught, then we end up with something that is a kind of silly, right? So the acceleration is 0, right? Well, I don't think that this model would be satisfying because it wouldn't really, it wouldn't coincide with what we see, right? So when you drop a rock, right, in a well, right, if the velocity, initial velocity is 0, right, and then the acceleration is 0, then so what would happen here? So here, just for the fun of it. So this means that this would be V0t plus H in 0, right? Okay. So basically, if we would measure, you know, so what I'm trying to say is that if we do the experiments with such a thing, we would notice that this doesn't go with the reality well, right? So we need a reality check, and then it ends up with fail. So there's not a good model, right? Okay, then another possibility is the other way around. So if Rg over V naught squared is much greater than 1, right? So i.e. much greater than V naught squared, right? Then let's denote in this case epsilon to be, so it's the inverse of this guy. So it would be 1 over, if you want, Rg over V naught squared. So the point is that then our model, right, will become something like, so let's put here this one 2, okay? So 2 becomes epsilon d2h dt2 equals -1 plus h squared. And again, you know, is epsilon is almost 0, then we end up with 0 equals 1, okay, with minus whatever, minus or plus, right? So 0 equals something that is, here, put the minus just for your sake, that is non-zero no matter what h is, right? So that's the right-hand side is never 0. So this is just, you know, completely inadequate, right? So it's just, right, impossible. Okay, so that model is completely out of okay, consideration. And finally, okay, what about if RG, right? I had to put this one in. So over V naught squared is more or less a 1, right? Then we end up with D2H over DT2 equals minus 1, 1 plus H squared, okay? And H in 0 is 0, DH dt in 0 is 1, okay? So this model might be, you know, just kind of all right, okay? But, okay, again, I'm gonna do a reality check. Okay, so maybe we should have done this at the beginning, but you know, I wanted to go over these cases just for the fun of it, right? So in reality, RG is about, so I looked for the numbers, 6,007, okay, whatever. So 6,371 kilometers, which makes it like 6,371 times 10 at 3 meters, okay? And then times, let's say, 10 meters per second squared. So basically, this guy is something like whatever, 6,371 times 10 at 4 meters, yeah? Squared per second squared, okay? And then V naught, right? Now we're pushing this rock down the well, right? So how fast can we push it? Okay, so how fast do you think we can push it? Because we're not, I don't know what super Star Wars lightsaber thing is, right? You know, I'm thinking that it's really fast when it shows up, right? Okay, so I don't know, 10 meters per second, 100 meters per second. How fast can we shoot it down, right? So no matter what we put, I don't think we're gonna get to something like this, right? So let's say it's 10 meters per second. So, you know, this would be about 10 at 2 meters per second squared. So the point is that in this story, actually, RG is kind of much greater than V naught squared. I don't know even what the order of that one would be, right? So in here, in this story, we would be, in this case, 2, which obviously led to something completely silly, right? So, but I wanted to go through the 3 cases just for the fun of it, right? I could have said, look, in reality, that's what kind of estimate we have. So, you know, that's what kind of thing we should do, but then we end up with something false. So, you know, or impossible. So, okay, so this choice of scaling is not good. So we have to go back and try a different scaling, okay? So here, this one was whatever, right? Choose this one. Okay, let's try a different choice now. 2, okay? So in 2, okay, let's say I'm gonna choose something. Again, okay, maybe I should put the, where is my fellow? Okay, so I'm gonna put the system up here, again, just to look at it. You don't have to write it. DC squared G over HC plus, and I'm not putting the bars, right? No bar, no bar. There you go. Okay. Squared, right? Okay. CV naught over HC. Okay, so that was the system 2, right? That's how we called it. Okay, so now choice number 2. Okay, so now we're going to choose something that is going to make this term here to be 1. So choose TC so that that guy is 1. TC squared G over HC is 1. So i.e. I'm going to choose TC. I didn't want to write it directly as root of HC over G. And then again, we have to choose HC, right? So again, I'm going to choose it R because it's so nice, okay? But this means that, okay, so that means that this is TC would be root of R over G and HC would be R. And then again, we're going to go back into the system, right? Into substitute into 2, right? Do the job. And then we end up with, okay, D2H, we kind of know what we end up with on the top one, because that's why we chose this one to be 1. Huh? So it's minus 1 over 1 plus H squared, okay? H in 0 is 0, but dH dt in 0, this one becomes something like this, okay? All right. Oh, you say, oh, that looks kind of okay. Well, I'm going to go back to the previous page in a way, okay? So again, we're going to observe that, okay, reality check is the one from the previous page, that RG is a kind of much bigger than V naught squared. So in this case, we on the end up that V naught over GR is a kind of 0 almost for a lot of initial velocities, right? And this means that somehow this one will always be a kind of 0, no matter what V naught is in a small range, right? And now we're on the Earth and we're saying, well, our V naught that I'm pushing the rock is not, I don't know what, terribly high. It doesn't compare with the product of RG, right? That's the main idea. So in other words, this model will fail, not because the equation is ugly or it goes to something like 0 equals something not 0, but because here it's independent of the velocity that we push in with, right? So no matter what velocity we're going to put in, it's always 0. You see, and it would be okay if it would be 1 in because then you say, oh, it's 1 because we adimensionalized the system, we scaled it. But when you put it 0, it's like you always have a non-contribution from the velocity in your model, which reality tells us, well, how could you have no contribution when you push a rock in the well? Because if you push it faster, it will reach the bottom faster, right? I mean, come on, right? Whereas if you just drop it, it will take a little bit longer. So that's why the model fails in this case, okay? It's an art in this scaling. It's not straightforward. It's not an algorithmic way. It has some you know, contribution in it. There is a contribution of intuition, right? And common sense, lots of common sense. Okay, so now we're going to go to the third model. Okay, so what we're going to introduce here, we're going to again make an observation, okay, that R is large. We know this, right? And so one thing is for sure that the radius of Earth is large compared to the distance that we're measuring. And then this characteristic time should be of order of the dropping time, right? So should be of the length, the time length or time interval of drop, right? So how long it takes for it to reach the bottom, to reach the bottom, right? So is this observation, right? We would think that, so maybe, okay, we would have R equals this TC times V naught, okay, velocity times whatever, right? Yeah. Okay, just a second. I'm missing something here. Am I missing something here? Or my notes are written a little bit off. Just bear with me. So, yeah, okay. So we should have something maybe like, yeah, for this one, let's take this one out. Okay, would be more like TC, right? Would be more like, let's see. G over V, okay, V naught, and HC, that's where the big change is. In HC, we're gonna change this one to be V squared and the G up there. Okay, looks a kind of weird, huh? So, so this is, well, yeah. Okay, so now if we go again and substitute, into 2, okay, so 2 was our system, okay, so we do the job and then we end up with something that will look like this. D2H over DT2 equals -1 plus V naught squared over GR H squared, and then H is 0, and dH or dt, let me write it nicely. dH or dt in 0 is 1. So somehow here, you know, is this term here, right? Let's see where it is. Right. This guy here, that is a kind of mysterious, but then this guy is actually our epsilon from before, right? So where did we do it? This epsilon guy, right? So I'm gonna put double star on it and bring it over, right? So this is actually our epsilon guy by double star. So this epsilon, remember, was small, right? So epsilon almost 0. So we end up with this model. Okay. And then H in 0 is 0. And then dH or dt in 0 is 1. And this is the model that uh, corresponds to the one with constant acceleration that we do in calculus, right? So this is the adimensional version of d2h dt2 equals minus g, right? So that's how it goes after we scaled it. Well, we took the Newton's gravitational law, we do the right scaling, and then we end up with the adimensional version of the model that we study in calculus or in first year physics. Okay. Now I repeat, you're gonna ask, so how do you know to take these guys? Well, it's the art of it, right? You know, and it depends from a problem to another, and you know, context to another. For certain material, or in certain contexts, people already know what the, you know, kind of scales are appropriate, right? For fluids, for whatever. Okay, so that's the thing. So now I'm going to go over these examples with dimensional analysis and the introduction of primary and secondary variables. In a way, you already know what are this, okay? So the idea is the following: when we model something, right, you have the physical variables, right? In this example with the pendulum that you have in front of you, there are 7 quantities in there, right? The physical variables. So, you know, the parameters and the variables, 7 of them. And then you have 3 fundamental units, right? 3 fundamental dimensions. So overall, there are 3 independent dimensions, if you want, and 4 dependent ones. So now we could choose, you know, as independent dimensions to be length, time, and mass, at power 1. But we could also be free to choose combinations of these 3, as long as they're 3 and they're independent, right? And those will be called primary variables. So in this problem with the pendulum, right? So we have a pendulum hanging, right? And it's a little mass blob there, right? So mass M is pulled down by G, L is the length of the pendulum, phi is the angle with the vertical. And we want to say something about the period, as it would depend on the angle. And then, so obviously there is a dependence on the angle, but then we have these parameters in the problem. We have the length of the pendulum, the gravitational constant, the gravitational acceleration, the mass, the initial angle, and the initial velocity, right, that is pushed down with. So can we say anything about the period? Basically just doing dimensional analysis on this problem. But what will be done differently this time, I'm going to leave this unit time, this period, on the left-hand side. I won't say f of all of them equals 0. I'm going to just let this t to be on a side, okay? And then I'm going to organize the dimensions of all these guys on this right-hand side in such a way that I know that they better be, when I do the algebra here with these powers, I should get just time on the right-hand side at power 1 as is time at power 1 on the left-hand side. So by now you should be experts in this stuff in a way. So the angles have no physical dimension, so I don't have to worry about them. The variables with dimensions are the period that I'm, you know, I want to say something about, the length, the gravitational constant, mass, and velocity. Fine. Okay. So here, when I'm writing the relationship between the dimensions of this thing, so I have time on the left-hand side is the same as this TP, right? It's time. And then here are the these physical variables with their own dimensions. So length, right? G would be at power 2, mass at power R3, and then velocity at power R4. And now, you know, probably I'm going to express these guys in terms of the fundamental dimensions like we did it before. There you go. Just I didn't put the square brackets anymore, but it's exactly L is L. G is LT minus 2, M is mass, V naught L over T. Fine, I'm writing them. Here is the system, right? And in this case, right, I better be careful. So the time here, see, so this, there is no L on the left-hand side. So these guys have to be add up to 0. Cool, okay. There is time at power 1 on the left-hand side. So these guys better be 1. Okay, fine. There is no mass on the left-hand side, so R3 better be 0. So that's where, right? That's how this system is conceived, right? And then we solve it, right? Again, you know, we're gonna have here, we have 4 unknowns, 3 equations, right? Anyhow, we solve it. And now at the end of it, here is what we get. We have that R4, if you want, is an independent variable, so it can be anything. And now it comes the game. Okay, so now I can choose the primary variables, right? So I can say is L at power 3 or L at power 1 or G at power 3 or GV naught together, right? So they're choices. But I'm going to choose in this example T, L, and G as primary variables. I'm killing the velocity, so I'm doing R4 equals 0. So there you go, right? The relationship between the period and the length and gravitational constant of the thing, right? Isn't that cool? Let's see, right? So here, we ended up with this. So the time equals root of L over G, and then times some functions that has no dimensions, right? So actually, if you did physics, you'll know that this is actually quite close to reality, right? And then from an experiment to another, we can say something how we conclude, right, that the period depends directly proportional with the root of the length of the pendulum and inverse proportional with the root of the gravitational constant. Interesting, huh? So that's the thing, right? So here, let's say G. So here I did a little back of the envelope thingy, right? So if the length is 100 meters, it's compared to a length of 1,000 meters, which would be a very long pendulum, right? And then you know that, you know, the period of the longer pendulum is 10 times longer than the period of the short pendulum, right? Without really knowing any kind of mechanics of the phenomenon, right? So here you have another example of how to deal with this a dimensional thingy, right? Non-dimensionalization, but to do it in a way that is bringing some information to the problem. So I repeat, this idea with the primary variables is what we want to choose to express. There is some freedom, right? Because these systems, you know, are having more than one solution, right? So there are infinitely many solutions. Of course, you know that you have a choice of how to represent the solutions, right? You know, because they're, you know, in a subspace of the space, right, of variables, and then you can choose different directions within that subspace, right? So if the subspace is two-dimensional, it's like R2. So I can choose two vectors in R2, could be the two axes or could be two, you know, crooked vectors. As long as they're linearly independent, they're good enough, right? So it's equivalent to this kind of choice of primary variables, okay? All right. So again, I'm going to cut this thing. Ryan, are you with me? Yeah. Okay. So I don't know how clear I am about this thing. So again, I repeat, there is a freedom when we choose this you know, the powers there and how to put this LT. No, the combinations of LT and M in this model, for instance, I could choose because I have freedom in choosing R1 and R2 to be. So I'll get, you know, for R4 equals 0, I'll get this kind of solution, right? Whereas if I take R4 equals 1, I will get the period that it depends on V naught as well. But that's not in my interest in this problem. My interest is to reduce as many as I can, right? I could actually kill the G in this problem, right? So I could choose, let's say, R4 to be actually -1, right? So then it will be, T would be L at 1/2 plus 1/2, huh? Right? And then is G at 0. That's why I chose it, right? So I want to kill this term here, right? So I'm choosing R4 to be -1. That's what I was saying. Right? Right? So then this becomes at power 1, right? Because it's minus 1 is 1. So this is not here, and then we'll have V naught at -1. So basically I can write the same period to be like L at 1/V naught, right? But now I'm choosing as primary variables L and V. That's the difference, right? That's where I'm saying that there is a choice there. So in the example that I wrote nicely, the primary variables were L and G, right? But now I can maneuver it, and I can say as primary variables L and V naught. And I killed the other one. I killed the G. So that's where this idea of primary and secondary variables is coming from, is the freedom of what you want to choose.